morning, everyone. We are Group 1, and our project is titled Designing Tactile Learning Tools via 3D Printing Technology. Our group designed a tactile heart model that helps vision-impaired learners understand heart anatomy through touch. In this presentation, we will explain the principles of 3D printing, the design process, challenges we faced, and how our final model supports inclusive education. Our group comprises of myself, Rebecca, Elvis, Claudius, Sayad, Salim, Zini, Kalista, and Alia. Traditional anatomical diagrams rely heavily on sight. This creates barriers for vision-impaired learners. Our goal was to convert the complex structure of the human heart into a tactile model that can be explored through touch while maintaining anatomical accuracy. 3D printing, also known as additive manufacturing, is the process of creating three-dimensional objects layer by layer using a digital design. This technology allows rapid production of customized models and has become increasingly important in education and healthcare.
So now we will be speaking about the principles of 3D printing. So to understand the principles of 3D printing, we just need to know the specific devices that aided us in the creation of 3D printing products. First thing, we have the SLA, which is like a UV laser that traces the object's, intricate details over a vat liquid polymer resin to get accurate measurements and solidifying it layer by layer as the build platform lowers after each press. And then we have a FDM, which is like a heated nozzle that feeds thermoplastic filament through, melts it, and extrudes it into the build platform in continuous lines from bottom to up. This is the most generic and most popular found version. And then we have the SLM, which is a high-powered laser that melts and fuses metallic powder particles together layer by layer inside a sealed atmosphere. This is like some of the high-end stuff. And then we have some EBM. It's like SLM, but instead it uses high-energy electron beams instead of a laser. This is more expensive but in more specific and detailed for high quality and very detailed products. The build runs in a vacuum, so no oxygen, which reduces residual stress in the finished parts. And then lastly, we have LOM, which is adhesive coated sheets of materials which are bonded layer by layer. A laser or a knife cuts the exact outline of each layer before the next is added. So let's talk about how biomedical applications can be used through 3D printing. The first part is surgical planning. Surgeons can 3D print exact replicas of organs to rehearse complex operations before making an incision. Next would be prosthetics and orthodontics, which is 3D printing rapid, affordable, lightweight, and custom prosthetic limbs, especially for children who need frequent changes. We can also use them for implants and dentistry by using porous titanium implants, which is used for aligners, crowns, surgical guides, and dentures. Bioprinting by using bioinks, which contain cells and growth factors, to imprint them into tissues that replicate skin, cartilage, and vascular networks. And lastly, pharmaceuticals by making custom pills, which combine medications or adjust dosages and release rate for one patient's specific needs.
We created a new model, learning from the failures of our first prototype, where the braille was too difficult to read, the model was too flat and thin, and the tactile features lacked clarity. In our final printed heart model, we have thicker raised lines, better tactile feedback, and improved durability. However, our braille is too thin and tall to read. Vision impaired learners can use it by locating the ventricles, following raised outlines, reading the braille labels, and also understanding the relationship between structures.
Presents the accessibility features of 3D Heart model, which was specifically designed for blind and visually impaired users. The model includes raised anatomical outlines that allow users to identify different heart structures by touch instead of relying on vision. They can explore the shape and position of each anatomical feature using their fingertips. Pre-labels are added to help users independently identify the names of the heart structures without requiring assistance. The tactile layout is kept simple and organized, making it easier to follow the anatomy step by step and reducing confusion during learning. Finally, the model is made from durable material so it can withstand frequent handling in classrooms, laboratories, and also independent study. Overall, these accessibility features promote inclusive education by providing blind students with an equal opportunity to understand heart anatomy through hands-on tactile learning. During this project, we faced several challenges. First, it was difficult to convert the complex anatomy of the heart into a tactile model that blind users could easily understand. We also need to maintain biological accuracy while simplifying the design. Another challenge was determining the right thickness for each structure so the model would be both durable and also easy to explore by touch. We also had to learn Tinkercad from scratch to create and edit our 3D design. And lastly, our first print failed, so we have to revise the design and printing settings before successfully producing the final model. Despite this challenge, each obstacle allowed us improve the final product and create a more effective learning tool for blind students. For future improvement, we have several ideas to make our 3D tactile heart model even more accessible and effective for blind users. First, we plan to integrate braille labels more systematically so that every anatomical structure can be identified more easily. We also aim to create modular heart components that can be assembled and explored individually. In addition, QR codes could provide audio explanation, giving extra guidance during learning. We would also like to use different textures to represent different anatomical structures, making them easier to distinguish by touch. Finally, we plan to use PETG instead of PLA because it's stronger, more durable, and better suited for frequent educational use. In conclusion, this project shows that 3D printing can improve accessibility in anatomy education. By combining tactile learning with universal design principles, we can support blind students while creating learning tools that benefit all learners.